Hello. This podcast is about analyzing velocity time graphs. First, we'll look at how we create velocity time graphs from position time graphs, and then we'll see how we find displacement and path length from velocity time graphs. Let's talk about how we create a velocity time graph from a position time graph. Here we have our position time graph. The object is starting at position 2 meters, positive 2 meters. It's moving in a positive direction for the first 4 seconds. Then it stands still for the next 2 seconds, and then it heads back towards the origin, so it's going in the negative direction for the remaining 4 seconds until we reach 10 seconds. So how do we go ahead and convert this into a velocity time graph? First, we need to analyze the slope of each line segment, because that will tell us the velocity. So for instance, if we find the slope of this segment from 0 seconds to 4 seconds, it will tell us the velocity. If we remember, slope is just simply rise over run. We marked out our run, which goes from 0 seconds to 4 seconds, and our rise, which goes from 2 meters to 10 meters. So our rise is 8 meters, our run is 4 seconds. If we do the calculation of slope, rise divided by run, we get 2 meters per second. So from 0 seconds to 4 seconds, the velocity of the object was 2 meters per second. Now we need to go over and show that on our velocity time graph. It's a constant 2 meters per second from 0 seconds to 4 seconds. So we draw this flat line from 0 seconds to 4 seconds at the 2 meters per second. Well, next we need to look at this section from 4 to 6 seconds. It's a flat line, so it has a run of 2 seconds, but it has no rise because it's flat, because the object was standing still, wasn't changing position. This had a velocity of 0 meters per second. Now we have to go ahead and from 4 seconds to 6 seconds, draw our flat velocity line at a velocity of 0 meters per second. Next, let's calculate the rise and run for our last segment from 6 seconds to 10 seconds. The rise was negative 4 meters. Now you may be saying, why is it negative 4 meters? Well, remember, to calculate the rise, it's the final position, which is 6 meters, minus the initial position, which was 10 meters. So for this segment, the displacement was negative 4 meters. And the run was the final time, 10 seconds, minus the initial time, 4 seconds. When we calculate this slope, negative 4 meters, which was our rise, divided by 4 seconds, which was our run, we come up with a slope of negative 1 meters per second. That tells us that our velocity from 6 seconds to 10 seconds was negative 1 meters per second. So we need to draw a flat line at negative 1 meters per second from 6 seconds to 10 seconds. So this is how we go from a position time graph to creating a velocity time graph. Now let's move on and look at how we find displacement and path length from a velocity time graph. We're going to start and focus on displacement first, because finding path length is pretty simple once we understand the process for finding displacement. Here we've got our velocity time graph from the previous example. We're going to stick with this motion. To find the displacement and path length, they're equal to the area between the velocity line and the time axis. This is the velocity line, and this is the time axis. The displacement is equal to the area between those two. Well, we may ask ourselves why. Let's take an example. If I told you you were driving 30 miles per hour for 2 hours, how far would you have traveled? And you would have told me that you would have traveled 60 miles. How would have you gotten that? You would have taken your velocity, 30 miles per hour, and you would have multiplied it by the elapsed time. In other words, how long you were driving the 30 miles per hour, and that's 2 hours. And that would have given you the distance, or in physics we would call that the displacement. So this formula, the displacement, is equal to the velocity times the elapsed time. Let's see how that relates to our velocity time graph. To find the area of a rectangle, it's the height times the width, and that'll give us the area. Looking at the graph here, we can see that the height of this rectangle is the velocity, because the y-axis is the velocity. And the width of this rectangle is time or elapsed time, because that's what's plotted on the x-axis. So when we find this area on the graph, we are taking the height times the width, but for this graph, that's the same as taking the velocity times the elapsed time, and we know that that gives us displacement. The reason the area under the velocity line is equal to the displacement is because the calculation for the area is the same as the calculation for the displacement. So let's take an example. From 0 seconds to 4 seconds, let's find the displacement. Well, to do that, we need to find the area under the velocity line from 0 seconds to 4 seconds. Well, that happens to be this shaded area. We need to take the height times the width. The height is 2 meters per second, and the width is 4 seconds. So when we multiply those together, 2 times 4 is 8, and when we do the math on the units, we have meters, but we have seconds in the denominator and seconds in the numerator. So these 2 seconds divide out to be 1, which make them disappear, and we're left with meters. So the displacement is 8 meters. Let's take a look at some other examples. Let's find the displacement from 4 seconds to 6 seconds. Well, that's this line here. Well, notice it's not an area. If we go to find the height and the width, notice the line has no height. So the height is 0 because the velocity is 0 meters per second, and the width is 2 seconds. But anything times 0 is 0 meters. And that makes sense. The object wouldn't have moved at all. It would have had 0 displacement because it was standing still when the velocity line was on 0 meters per second. Let's find the displacement from 6 seconds to 2 seconds. That involves this velocity line from 6 seconds to 10 seconds. This velocity line is below the time axis. Remember, the time axis is where the velocity is equal to 0. So we need to find the area below, and that's this shaded area. So we have our height, which is -1 meters per second. And we find our width, which is 4 seconds. That would be 10 seconds minus 6 seconds. And when we multiply this, the area is -4 meters. And that means that our displacement from 6 seconds to 10 seconds would be -4 meters. Suppose we were asked to find the displacement of this entire time from 0 seconds to 10 seconds. Well, what we would have to do is find the area under each different velocity line. Notice there's 3 different velocity lines on this segment from 0 seconds to 10 seconds. We would have to find the area of this, which we already did, 8 meters. We'd have to find the area of this segment, which is 0 meters, and we'd have to find the area of this segment, which is -4 meters, and we would need to add them together. And when we add them together, we would get the displacement of 4 meters. That makes sense because initially the object was going 2 meters per second in the positive direction for 4 seconds, so it traveled 8 meters. Then it stood still for 0 meters. And then in the last 4 seconds, from 6 seconds to 10 seconds, it would have moved in the negative direction back towards the origin at a velocity of 1 meter per second in the negative direction. And so that means the total change in position would have been 4 meters. Let's go ahead and look at another example. We have our same graph here as before, but now we want to find the displacement from 1 second to 3 seconds. We still want to find the area between the velocity line and the time line, but we only want to use the part of the velocity line from 1 second to 3 seconds. We're not looking for the area under the entire segment here, but the segment from 1 second to 3 seconds. That has a height of 2 meters per second, and it has a width of 2 seconds. And when we do the math, that gives us a displacement of 4 meters. Let's move on to another problem. Find the displacement from 4.5 seconds to 5.5 seconds. Well, that's this segment here, so it's part of this velocity line that is on 0 meters per second. We need to take the height times the width to find the area, but notice this line has a height of 0 because it's on the time axis where velocity is equal to 0. The width is 1 second, and 0 meters per second times 1 second is a displacement of 0 meters. Suppose we were asked to find the displacement from 7 seconds to 9 seconds. That would be this section of the velocity line, the height times width of this area. And again, because the velocity line's in the negative region, we have to draw this area or rectangle going from the velocity line up to the time axis. The height is -1 meters per second, and the width is 2 seconds, and when we multiply that, we get -2 meters. So from 7 seconds to 9 seconds, the object would have moved in the negative direction 2 meters. So let's move on with another problem. Find the displacement from 2 seconds to 8 seconds. In this problem, 2 seconds to 8 seconds goes across all three of our different velocity lines. So let's see how we solve this. This is a little different than the other problems. First, we need to find the area for each velocity line. Area 1 is going to be the width and the height multiplied by each other, and that's shown here. Now I used a different color just so we can see the three different segments. Notice from 2 seconds to 4 seconds. This velocity line ends at 4 seconds, so we have to stop this area at 4 seconds. And when we do that, it's 2 meters per second times 2 seconds, which gives us a displacement of 4 meters for this segment, 2 seconds to 4 seconds. We need to keep going on. Area 2, well, we've seen in previous examples that from 4 seconds to 6 seconds, there was no displacement because the object did not move. Let's go ahead and look at area 3, the height and width of area 3. Well, we start at this third velocity line, but our 8 seconds comes before the end of the velocity line. So we're only interested in finding the area between the time axis and the velocity line for this section, 6 seconds to 8 seconds. And the reason for that is we were just asked to find the displacement to 8 seconds. And when we do this, we have a height of -1 meter per second, a width of 2 seconds, and that gives us an area of -2 meters. We found the areas of our three different velocity segments from 2 seconds to 8 seconds. It gave us, because we have three different velocity lines, it gave us three different areas. The first area was 4 meters, the second area was 0 meters, and the third area was -2 meters. To find the displacement from 2 seconds to 8 seconds, we need to add those displacements up. And so 4 meters plus 0 meters plus -2 meters gives us a total displacement of 2 meters. So the object moved 2 meters to the right from its original position. Let's move on and find out how we calculate path length from a velocity time graph. So once again, we have our same motion represented by this velocity time graph from 0 to 10 seconds. To find path length, we're going to follow the same process we used for displacement, but all areas will be positive. Even the areas below the time axis will treat as positive areas. And we do that because path length is a scalar quantity, so it has no direction. And remember, the positive and negative in physics are not to tell us the value, but to tell us the direction. In this problem, we're asked to find the path length from 0 seconds to 10 seconds. So that's going from here all the way over to here. We have 3 different velocity lines. We need to find the area between the time axis and the velocity line for each of those 3 lines. So our first section is 0 to 4 seconds, and that's represented by this area. And of course that's 2 meters per second times 4 seconds will give us a path length of 8 meters. Then our next time segment is from 4 seconds to 6 seconds. Well, that represents this velocity line at 0 meters per second, and we know that's going to leave us with 0 path length. And then finally, we have to go from 6 seconds to 10 seconds, and that is this area below the time axis. When we go to find path length, the height is 1 meter per second, not negative 1 meter per second, because path length is a scalar quantity, so there is no direction. There are no positive or negative directions. So 1 meter per second times 4 seconds gives us a path length of 4 meters. To find the path length for this entire time interval from 0 seconds to 10 seconds, we simply do what we did before for displacement. We add up all 3 areas. So we have 8 meters plus 0 meters plus 4 meters gives us a path length or distance of 12 meters. So the object in 10 seconds moved 12 meters. This ends our podcast on analysis of velocity time graphs. I hope you found this helpful. Have a good day.